In this video, we're going to take a deep dive into looking at the structure of a molecule called benzene and some of the physical and chemical evidence that supports this particular structure. So to start out with, benzene is C6H6 and it's called an aromatic hydrocarbon. So we can take a look in other videos on different hydrocarbons and why this is in particular an aromatic hydrocarbon. But for now, we just need to know that it is an aromatic hydrocarbon. Its Lewis structure is a 6-member carbon ring with alternating single and double bonds. Okay. Now, since we have this alternating single double bonds, we can draw two possible resonance structures, which means that there is delocalization. So very important to note, whenever we have different resonance structures, we always have delocalization. Now, this can be condensed down and shown with just a stick kind of model here. So as we're kind of interpreting this, each of the points on here is a carbon, and carbon always forms 4 bonds. So we have 1, 2, 3. We can picture that there's another hydrogen there, and so on and so forth for each of these. So this is just another way to represent a benzene molecule. Now we can also draw a resonance hybrid. So I'm going to draw a hexagon. And typically what we do is we show dotted lines for the electrons that are delocalized. But in benzene's case, typically it's drawn with a solid circle inside. So it should really have the dotted ring, but commonly, convention, we always draw it with a solid ring. Now let's take a closer look at the delocalization that's happening in benzene. So because we have this alternating single-double bond kind of structure, there is 1 electron in each of the 6 carbon atoms that's going to occupy a p orbital. So we'd have like 1 electron. I'm drawing it in the top lobe, but we don't know where it is. I'm just drawing it there for sake of clarity. That's occupying those p orbitals. And so those 6 p orbitals can do side-to-side overlap with each other. And when it does that, it shares those 6 electrons equally amongst all of those different p orbitals. And it creates almost like this donut ring of electron density above and below the plane of the molecule. So the carbon part of the molecule, because each carbon has 3 bonding elements and no non-bonding elements, it would form a trigonal planar shape. So the ring itself is planar, and then we have this electron density above and below the plane of the ring. And the electrons in this ring are delocalized. We say that each of these carbons, and we'll get into this in another video, but for now, just know they're sp2 hybridized, and we'll come back to that concept in a separate video. So there's some really great physical and chemical evidence for delocalization in this benzene structure. So let's start with the physical evidence. And the physical evidence is fairly easy. So if we were to look at a carbon-carbon single bond length is 154, and the bond enthalpy, or the energy it requires to break that carbon-carbon bond, is 346. Whereas a carbon-carbon double bond is 134 in length and 614 for its bond enthalpy. Each carbon-carbon bond in benzene is intermediate. So it's 140, which is between these two values here, and its bond enthalpy is 507, which is between those values there, meaning that the bond length is between a single and a double bond, both in the length and in its strength. So that's some pretty compelling evidence for the structure of benzene. Now, we also have some chemical evidence for delocalization, and we're not going to get into too much of the weeds about the reactions that are happening here, because we're going to do those in some separate videos. But know right now that if a compound, an organic compound, has a double bond, these are known in a class of family called alkenes, okay? And if we're saying benzene has double bonds, true double bonds in it, they would undergo what's called an addition reaction. And so if that was the case, it would break one of the double bonds to add chlorine if we were reacting this with chlorine across that double bond. However, benzene does not do these reactions. So this is not the case for benzene. Instead, benzene undergoes a type of reaction called substitution. And substitution reactions are just taking one of these hydrogens here, and if we were to react this with chlorine, it's just substituting one of those hydrogens with a chlorine. Now, the reason for this being is that substitution reactions are going to maintain the additional stability of the delocalized ring of electrons. And so that is why benzene prefers substitution reactions over addition reactions. Now, some further evidence for delocalization structure is if we take a double bond and we do a type of reaction called hydrogenation. So that's adding hydrogen across a double bond, and it's going to break the double bond, add hydrogens there, so you're left with a single bond. And so if we took a look at a ring structure with just one double bond, and we added hydrogen, it takes about 120 kilojoules per mole to do this reaction to break that double bond and create our single bonds. So we've added an extra hydrogen across this double bond. Again, doesn't really matter about the specifics of the reaction right now. We're just kind of going through the chemical evidence here. If we were to take a look at a ring structure that has two double bonds and we add 2 moles of hydrogen, that's going to take 240 kilojoules per mole. So essentially it's double the first reaction because we're doing this reaction twice. Now, if we were to then take benzene and predict if we added 3 hydrogens, so breaking those 3 double bonds, we would predict it to take 360 kilojoules per mole. However, when we actually measure this, it only takes 208 kilojoules per mole. And so one thing to kind of keep in mind is the greater the amount of energy that is released, the less stable the reactants are because they're all forming the same product. So the difference between these two here, it's about 152 kilojoules per mole if we did the math. So what that means is that benzene is much more stable, and this is due to the delocalized ring of electrons. And that's because we have reduced repulsion compared to electrons in fixed bonding positions. So because of this difference in energy, it shows us that benzene is more stable, and so it's not going to take as much energy to do this particular reaction. And we have one last piece of chemical evidence that we need to look at for this delocalization. So when we react, if we were to react chlorine with benzene to form a 1,2-dichlorobenzene, so we're adding chlorines across a double bond, you might expect 2 possible isomers to form. So again, it doesn't matter about the details of this particular reaction, but we could have an isomer or one of our structures where the chlorines are adding across a double bond, and the other one could be a possibility where we have the chlorines added along a single bond. And this would be the case, like this is what we would predict if there was no delocalization. However, doing this reaction, there's only ever one isomer formed, so only ever one sort of structure formed, and that's because all the electrons are evenly distributed. So these 2 isomers actually just represent resonance structures of the same molecule. And it's actually better to just draw our resonance hybrid here where we've got our two chlorines like this. So these are actually the same molecule. Okay, so benzene has a lot of really great physical and chemical evidence for delocalization, and we've shown that here in this video. So that's it then for this video. We'll see you in the next one.